Hello, good morning, good afternoon, good evening, ladies and gentlemen. Welcome to this series of tutorials. If you haven't already, subscribe to the channel, leave a like, comment, and share. Now, in today's video, we have a very interesting theorem, and that is Picard of existence and uniqueness theorem. So this theorem helps us to determine beforehand if differential equations will have a solution and if that solution will be unique. Right, so I'm just going to provide the proof of the theorem, then in later videos we'll see the application. So the theorem says, suppose we have a function f and its derivative that are continuous on a rectangle D. So this is a rectangle D with the vertical y minus y naught less than or equal to b, and the horizontal t minus t naught less than or equal to a. And if f is Lipschitz on y, and that is if f satisfies the Lipschitz condition, then the initial value problem y prime of t equals to this with an initial condition that has a unique solution on D, right? So that is the theorem, and what we just need to show are a few things. That is, if f is continuous, if f is continuous, if f of t comma y and d of f t comma y dt are continuous, then f is Lipschitz or satisfies Lipschitz, or say is Lipschitz. Okay, so this is the first thing that we'll have to verify. If f and the derivative are continuous, then f is Lipschitz. Secondly, we would have to verify that the solution of y prime exists in D. Okay, that is the second thing that we'll verify. Then the third thing we'll verify is that the solution is unique, and we are done. So if we verify this, then we have verified that the solution is unique. So we'll see about that. So let's start with verifying that given that f and the derivative are continuous, then f is Lipschitz. So this is very easy to prove. So we'll consider f as a maximum m. So m is the maximum of f, and L is the maximum. The derivative will have a maximum, and that's so consider which has y naught minus y minus y naught less than or equal to a, and less than or equal to b, and t minus t naught less than or equal to a. Then we'll choose a that is less than the minimum of the bounds in B over the maximum and 1 over L. So we'll choose the smallest value of A that we can choose so that it remains inside. Now, if we have this and we suppose t comma y1 and t comma y2 are 2 points in D. Okay, if these are 2 points in D, then by the mean value theorem, okay, so by the mean value theorem, f of t comma y1 minus f of t comma y2 is equal to the derivative of f at some constant c. So for c, that is between y1 and y2, something like that, or y2 and y1, wherever you put it. Then this is the case, y1 minus y2. Okay, so the mean value theorem verifies this. So, and if we introduce modulus both sides of this, we see that we're going to have that, and I can put modulus here and here. And now you notice that the constant, this is actually less than the maximum of f at y and t dt. Okay, and we know that this is L, so this is equal to L. So basically the derivative at the constant is less than L, so meaning that we can substitute this here and the inequality will change. So we'll have f of t comma y1 minus f of t comma y2 less than or equal to L. Then we have y1 minus y2, right? So we can have that. So that's Lipschitz condition. So therefore f is Lipschitz. So we have verified the first thing, that is f is Lipschitz. Now we need to verify that the solution of the initial value problem exists on the domain D. Again, we're going to get the same thing, so we'll let m be the maximum as already noted, and L be the maximum of the derivative, and we have the region this. So now we consider the initial value problem, y prime of t equals to f of t comma y. All right, now for this one we can integrate both sides from t naught to t, and this side from t naught to t. So we'd have to change this to s ds, something like that. So when we integrate on this side, we're going to have y of t minus y of t naught equal to the integral from t naught to t f of s comma y ds. So we have this, and when we introduce absolute values on both sides, okay, and if we want these absolute values to be inside, then this would be less than the integral from less than or equal to the integral from t naught to t, and the absolute value of f of s comma y ds, like that. So having that in mind, we know that this is a constant m, all right, and we can factor it out, and if we differentiate, if we integrate over t minus t naught, we can see that y minus t minus y minus t naught, which is just y naught, is actually less than the constant m, we say less than or equal to, and when you integrate over a constant, you're just going to have t minus t naught, and we can create a further bound like that, so this will still be less than that. So we have this, and we notice that t minus t naught is actually less than a, so we can further create a bigger bound on this. So we have y of t minus y naught less than or equal to ma, right? Now, since we said A is less than the minimum of B over M. So we see that AM will actually be less than B. So meaning that this is less than B. That shows that the solution of, okay, the solution Y will be inside the triangle since it will be less than B and less than MA. So the solution Y of T is in D. Okay, so we have verified that the solution exists in D. Now we need to verify that the solution is unique. Let's consider capital Y a set of all continuous functions. So we have a set of all continuous function Y from T naught minus A to T naught plus A, mapping onto the real numbers, such that the maximum of Y naught or Y minus Y naught, or the difference between the center and Y, that maximum is less than B. Okay, so if we have that, then we can conclude that this set of all continuous function is closed and is of a subset of T naught minus A comma T naught plus A, and thus it is a Banach space. It is a Banach space with a transformation of capital Y onto T naught plus A and T naught minus A, and we can define its transformation as T of YT equals to Y naught plus integral from T naught to T of f of s y of s ds. So we can do that. And for uniqueness, we just need to show that this transformation maps onto itself and it is a contraction. Then from there, we can conclude that y of t is a unique fixed point in B. So that is all that we're going to do. So we are going to show that T maps onto itself. We are going to get Y of T, which is just the transformation of Y of T. So I can erase that. And we will transpose Y naught. And we have integral from T naught to T of f of s y ds. All right. And we're going to show that the transformation actually maps onto itself. That is, it is less than B. Okay. And if we show that the transformation minus Y naught, the distance between the transformation and Y naught is less than B, then we can conclude that the transformation maps onto itself. So right here, we'll introduce absolute values on both sides. And if we want the absolute values to be inside the integral, this will be less than or equal to the integral from T naught to T of f of s y ds. And we have the absolute values inside here. And we know that this is a constant. It has a maximum m. So again, we're going to have T of y of t minus y naught less than equal to integral from T naught to T of m ds. Right, and we are integrating over a constant, so this will further be less than T of y t minus y naught will further be less than m t minus t naught. All right, and this is a, so this is a, so this is equal to ma, and a is less than b over m, so just like we showed. So we see that this is less than b, so this shows that the transformation maps onto itself. So we've shown that T of y of t minus y naught is less than b, So the transformation maps on itself. All right, so this verifies the first condition of Banach's. Secondly, we just need to show that the transformation is a contraction, that is the maximum is actually reducing. So if it is reducing, it is reducing onto y of t. So it will show us that y of t is a fixed point. So for this one, we'll take the difference between t of y1 t minus t of y2 of t. And this will be equal to the integral. So the constants will cancel out. So it will just be t to t. Then we have f of t comma y1 minus f of t comma y2 dt. Okay, so instead of t, let me put s, because when we integrate, we have to replace back t. So we have this, and same thing, introducing absolute values both sides. We are going to have this, and taking the absolute values inside the integral, we are going to have t of y1 t minus t of y2 of t less than or equal to integral from t naught to t of f of s comma y1 minus f of s comma y2 ds, like that. And by Lipschitz condition, remember this from Lipschitz condition. So this one is less than L, this is less than L modulus of y1 minus y2. So meaning that if we integrate on this, which is a constant, we would further have t minus t naught multiplied by L multiplied by y minus y naught being greater than this. So we can write this as t of y1 of t minus t of y2 of t. So this is less than L y1 minus y2 and t minus t naught. Okay, so this will be the case. So this, by Lipschitz condition, we have this. So this will be some constant, and if we integrate over a constant, it will just be t minus t naught. So we know what t minus t naught is, and we can take the maximum of y1 minus y2, and this will be less than, so t y of b, sorry, y of t minus t, this is y1 minus t y2 of t. So this is less than L, we know what this is, so this is A, and we're taking the maximum of that, so we say A and y1 minus y2, so the sup of that. So if we take the sup of that, and we note that A is less than the minimum of B over M and 1 over L. So this shows that A is less than 1 over L and AL is less than 1. So if AL is less than 1, this will be contracting. So meaning that we are going to have a contraction. Okay, so we say since AL is less than 1, and this one is less than this, so we're going to have a contraction. So it's less than 1, we have a contraction. Okay, so we've shown that y of t is a fixed point and it is unique. This is by Bernak's fixed point theorem. All right, so let me run through real quick, like on the general ideas. So first of all, we have the theorem, and we needed to show that if f is continuous, then it will verify Lipschitz condition. So we did that by the mean value theorem. Right here, we verified that it verifies Lipschitz condition. Then we, okay, right here, we need to use Bernak's theorem to show that if we choose a transformation onto y, then y will map onto itself and it will be a contraction. And if it maps onto itself and it is a contraction, then y of t is a unique fixed point. So we showed that y maps onto itself by taking t of y minus y naught, and we simplified. We found that this is less than b, so meaning that the transformation remains inside D, so it maps onto itself. Then after doing that, we needed to show that we have a contraction. So we showed that we have a contraction if the maximum is decreasing. So we found that the maximum is indeed decreasing, so we have a contraction. So we have verified all those points by Bernak's fixed point theory. Yt is a fixed point, that it is a unique fixed point. So that is about it for today. Have a great evening.